The following footage is sourced from the Creator Profile U.S. Department of Energy at archive.org and is listed under Public Domain Mark 1.0. HYBLA FAIR was an underground, horizontal line-of-sight (LOS) weapons effects test conducted at the Nevada test site on October 28, 1974. The test had a relatively small design yield of less than 20 kilotons. This lower yield test was thought to be appropriate because an earlier, larger yield test caused loss of valuable data when the force of the detonation through the LOS pipe destroyed experiments. However, the HYBLA FAIR test had an insufficient yield to provide the amount of radiation necessary for the LOS experiments to perform as anticipated, and the desired data was not obtained. An LOS pipe allows scientists to take measurements of the effects of heat, blast, and radiation. The pipe has a diameter ranging from a few inches to as much as 30 feet. Inside the pipe, with the nuclear device at the small end, experiments are set up to be exposed to the radiation effects, but not the shock and blast effects. These effects are prevented from rushing through the pipe by fast-closing steel doors. Radiation travels faster than blast and shock waves, thus allowing the doors to close and the radiation tests to be conducted.
At the Nevada test site, the Defense Nuclear Agency conducts weapons effects tests so that weapon systems under development can be tested for their ability to withstand the effects of a nuclear countermeasure. HYBLA FAIR is a test of a new concept for conducting these tests. This new concept utilizes the output of a much smaller nuclear device than is presently used, and could result in both lower costs and reduced turnaround time between events. To create the proper environment and to comply with the Limited Nuclear Test Ban Treaty signed in 1963, all nuclear weapons effects tests are conducted underground. Most of these tests take place in the tunnel complexes under Rainier Mesa. In these tunnels, thousands of feet from the portal, test beds simulating the outer space environment are constructed. Present test bed configurations include a room housing the nuclear device and a tapered line of sight or LOS pipe. The nuclear device and the first several hundred feet of the LOS pipe are completely covered by a sand and cement mixture called grout. The LOS pipe may vary from 1,000 up to 1,700 feet in length and contains experiment protection devices in the first 500 feet. Connected to the end of the pipe are a series of test chambers which house the experiments. There are two basic requirements which apply to any weapons effects test bed. First, the experiments must be exposed to the proper radiative environment, and second, the experiments must be protected from possible damage by undesirable side effects. Because the test chambers must be big enough to accommodate large effects experiment packages, the HYBLA FAIR test chamber diameter of 84 inches or 7 feet is representative of the size that meets this requirement. This taper of about 0.8 of an inch per foot is nearly 6 times greater than the tapers for presently used LOS pipes. These design criteria impose several problems that need to be resolved in order to satisfy the requirements for an effects test bed. To illustrate the problems that may be encountered, consider what occurs during the test. When the nuclear device is detonated, radiation traveling up to the speed of light is emitted in all directions. A very small portion of this radiation passes through the aperture and travels down the LOS pipe into the test chamber. In less than 1/1,000,000th of a second, the experiments have been exposed. Now the experiments must be protected from the remaining energy released in the detonation. Hot gases generated by the explosion and pipe vaporization form a shock wave in the vacuum pipe. In present test beds, these gases are prevented from reaching the test chamber by fast closing doors which block the LOS approximately 300 to 400 feet from the device. In a HYBLA FAIR type of test bed, new, larger, and faster closures than are presently available must be developed to protect experiments. For this first test, there are no closures. Instead, the phenomena associated with the gases will be monitored directly to define the experiment protection requirements for events using this type of test bed. In both the HYBLA FAIR and present test beds, the grout or stemming material surrounding the front end of the pipe is forced into the line of sight by the ground shock wave which collapses the LOS pipe. The broken pipe and grout combine to form a gas-tight plug between the cavity and test chamber. When this stemming plug forms, the experiments are protected from the energy still within the cavity formed by the detonation. The successful creation of the stemming plug also serves to contain the radiation in the mountain. Should the stemming plug never form or be destroyed before the pressure in the cavity dissipates, additional tunnel plugs are needed to contain the radiation and prevent leakage to the atmosphere. These plugs at strategic locations in the tunnel are gas-tight concrete structures designed to withstand pressures and temperatures greater than any which could be caused by the worst conceivable failure of the stemming plug. Although no weapons effects experiments are on HYBLA FAIR, this test includes a large array of other types of experiments that will acquire data in three areas: the radiation environment in the test chamber, the properties and influence of the gas front in the LOS pipe and test chamber, and the phenomena which involve or influence stemming and cavity conditions. To determine the suitability of the HYBLA FAIR device as an effects test source, its radiative output must be well defined. In a series of pipe stubs behind the test chamber, the device diagnostic experiments will measure the energy spectrum and total fluence of the radiative pulse. An array of calorimeters in the test chamber will monitor the uniformity of fluence distribution across the test chamber. Never before has there been a greater requirement to define the conditions created by the high-temperature, high-pressure gases and other debris in the LOS. Sensors protruding from the pipe into the LOS will take advantage of this first-time opportunity to measure the pressure and duration of the gas front as it travels down the LOS. Inside the test chamber, detectors will monitor the energy and arrival time of the gas and other debris. Other instrumentation will record the reaction of the test chamber to the impact of the gas front and to the passage of the ground shock. Experiments located on the pipe will measure pipe wall motions, heat energy transferred to the pipe, and pressures on the pipe wall and in the stemming area due to the flow of the gas front. X-ray machines will measure the density of the gas front. High-speed photography will document the gas flow and its effect on the pipe, with one installation directly on the wall of the test chamber and another utilizing a system of mirrors which provide an optical path to a shielded alcove 200 feet from the pipe. The formation of the stemming plug appears to be a very turbulent phenomena affected by a number of factors. The HYBLA FAIR instrumentation is designed to provide data on the interaction of the gas front in the LOS, the motion of the mountain in the near vicinity of the tunnel, cavity growth, grout extrusion, and many other contributing factors. The larger yield devices used on present effects tests create such a severe environment in the stemming region that it has been difficult to monitor what occurs there. On HYBLA FAIR, with its smaller device, the less severe environment gives a much higher probability of survival to active gauges which transmit signals to remote recorders. Passive instrumentation is being installed as a redundant source of measurement, but data from these gauges will not be available until they are located by mining back into the stemming region during re-entry operations. Gauges located in the predicted cavity region are expected to measure pressures and temperatures in the cavity after complete cavity formation. Gauges in the stemming area will measure ground shock arrival times, stemming pressures, and the accelerations and displacements of the stemming material and the tuff near the stemming region. In the parent rock away from the pipe, gauges monitoring pressure, velocity, and acceleration are located at ranges predicted to be from about 150,000 psi to about 3,000 psi. Instrumentation cables from all the active gauges and sensors pass through the containment plugs and are connected to oscilloscopes and tape recorders in environmentally controlled containers inside the tunnel, in recording trailers at the tunnel portal area, and at the main trailer park on top of the mesa, 1,200 feet above the test bed. After months of detailed planning and preparation, the test was ready. At 0700 hours on the 28th of October 1974, the device was detonated. Moments later, the experiment drift and bypass drift experienced high temperatures, pressures, and radioactivity. A permanent gas-tight seal had not formed between the cavity and the remainder of the test bed. However, the gases and other debris were isolated within the mountain by the concrete containment plugs. Even with the rapid introduction of cavity gases and other debris into the test chamber area, the essential information being sought on HYBLA FAIR was obtained from most of the experiments. The total nuclear yield of the detonation was close to what had been predicted. These data indicate that the HYBLA FAIR test bed as designed would not have been a suitable test bed for an effects test based on the following conclusions. While the device yield appears to be up to expectations, the radiation environment it provided was inadequate. The velocities of the debris and gas flow exceed the capabilities of present experiment protection techniques. A gas-tight stemming plug did not form between the cavity and test chamber, thus preventing a timely recovery of experiments. HYBLA FAIR was a test of a radically new concept. This test has identified the problems associated with a low-yield nuclear device and a short, highly divergent LOS pipe. These problems must be resolved before complex and costly radiation effects experiments can be performed. However, much valuable information which was unavailable prior to HYBLA FAIR has been obtained on radiation output, pipe flow, and stemming behavior in a low-yield nuclear event. The new measurement techniques successfully developed for HYBLA FAIR are now being used on standard test beds to further our understanding of the phenomena which occur on an underground nuclear weapons effects test.